Want to point out to you, we didn't mention this last time though, if we look at the My Notre Dame page under the downloads, we have a digital copy of the textbook available there. If you prefer a paper copy, we'll talk at the end of the class today and I'll sign out a book for you if you want a book. That's fine. We got lots of them, so there's no shortage. But some people are just like, yeah, that's one less thing for me to carry around. But some people like having the book as like a security blanket or something, So I just wanted to point that out. I forgot to mention that last time. On the OneNote, you'll notice that I added some extra stuff in and moved some of these sections around a little bit. So I've kind of put in perspective, like after these many sections, we'll do a test, just to give you guys an idea. So some of the tests are going to wrap around from like one chapter to the next or whatever, just trying to break up what I know is the significant pieces into a more appropriate test size chunk. I know I talked about doing that the other day, and I thought about it a little bit more, and I kind of at least penciled in some perspective breaks as to when the test would occur. And let's take a little gander at this thing that I asked you guys to work on yesterday. So part one, when I glanced through, it seemed like everybody basically did this right. So I said just x equals a, so it didn't really matter where you put that horizontal asymptote, and I said x equals b. It didn't really matter where you put that horizontal asymptote. And then as far as your curve goes, most of us drew what would be called like a simple rational function, where like one end goes like this and the other end goes like this. Now you could have had them like kind of in any configuration, right? You could have had them both on top or both on bottom, or top corner and bottom corner. It wouldn't have really mattered, right? Like how you wanted to organize that. That's all going to be fine. No big deal. If I refer to each of the four end behaviors, I'm just going to call them like 1, 2, 3, and 4. For 1, you'd say this is the limit as x approaches. So if I look at this coordinate here, this is kind of like negative infinity comma b, right? So the x coordinate is going to negative infinity, and then I'll just call this function f of x, and the y coordinate should be b. So I'd write it that way. If I did the same thing for this arrow, the x coordinate there is kind of like a, and the y coordinate's negative infinity. But I have to be a little bit careful with this one, because if I write here, if I look at number 3, I'd say that x coordinate is also a. And I know that for something to be a function, we can't have two of the same x coordinates. That doesn't work. So we have to do something to distinguish one of those arrows from the other. So if I look at number 2, we would say that's like the left side of a. So that's x approaching a from the left. The way we designate that is we just put like a little superscript of a negative sign on the a. And when we read that, that's x approaches a from the left. And then likewise, 3 is the exact same thing, except it's going to be a from the left. I'm sorry, from the right. And it's pointing up, so it's going to positive infinity. Is this kind of ringing bells? This is what I was trying to jog your memories back to. And the point was not to make everybody feel stupid the first day, but to get you thinking about this stuff. And when we do it again here, it's going to be like, oh, yeah. That's what I was trying to get to. And it'll stick a little better. And then if I look at 4, again, that x is positive infinity and the y would be b. So limit as x approaches positive infinity of f of x is equal to b. So that's those are the 4 end behaviors you should have written. Now, obviously, if you drew your graph slightly differently, like, these potentially could be switched or both the same. But it's, like whatever. For the graph that we drew, that's how you would label those. Does that feel okay today? Yeah. If I asked you to do that again, it'd be like no problem now, right? But it was like, that was like 1.5 classes from like 6 months ago. I couldn't pull it, which is okay, right? Like that's not uncommon. And obviously the way I graded the homework quiz reflected that I didn't really care, right? I just wanted you to try something. All right. So the way this course in first semester is kind of set up, chapter 2 is all going to be about limits. So that's where we're going to start, is talking about limits and how do we evaluate a limit and how do we calculate a limit and what does the limit really mean. And then chapter 3 is about derivatives, and it's kind of like the theoretical side, like how do I do a derivative? What if the function looks like this or this or this? How do I do it that way? And then chapter 4 is like applications of derivatives. So like what kind of problems can I do, or can I use a derivative to answer, short of just like take the derivative of this, like it's application. Second semester, chapter 5 is about integration, or the integral. That's kind of the inverse operation for a derivative. Chapter 5 is like the theoretical side. 6 and afterwards is just like application stuff. So those are really the 3 key operations that we'll talk about in an AP calculus course, is the limit, the derivative, and the integral. Now that's all Greek to you at this point, aside from kind of the limit, which we talked about a little bit last year in trig and pre-calc, and maybe some of us have heard the term derivative before. If you talked about if you had an econ class, you probably talked about derivatives with respect to economic stuff. Maybe not. It doesn't really matter. We're going to do it all from scratch anyways, right? Which is all you need to know. All right. So we're skipping 2.1. I'm going to do 2.1 a little bit later. We're going to start in section 2.2. And in 2.2, we're just going to be talking about limits of a function. And there's going to be 3 ways that we're going to talk about how we evaluate a limit. So we're going to talk about how we do that graphically. So if I can look at a picture of the graph, you should be able to write down you should be able to tell me what the limit is. You should be able to use a table. So if I give you a function, you should be able to generate some points that'll end up telling you what the limit is. And then algebraically. So can I just look at the function and kind of piece that together? And that algebraic side will wrap into section 2.3. So that idea of how do I do this algebraically is going to wrap into section 2.3, where we really develop a lot of really helpful tools in order to do that algebraically, because that's what we'd like to do, right? If I'm given a function and I ask you to take a limit of it, ideally you don't want to have to generate a graph, especially if there's not a calculator available to you, which on the AP exam there will not be in certain sections. You don't have to generate points, like plug in values, especially values with lots of decimal points, because boy, that's a hassle, especially without a calculator. Ideally, you'd like to just be able to look at the thing and be able to kind of tell. And that's kind of where we want to head to. But before we're able to do that, we need some intuition, and pictures help me a lot. And numbers, like definite numbers, help me a lot to build some intuition out. So that's kind of where we're starting. Okie dokie. All right. So we'll start just with the general question of kind of what is a limit? So our definition, this is the first definition for a limit we're going to get. We're actually going to get a second one later on, because I'm going to do 2.4 is going to be just like a little toe. We're going to dip our toe into 2.4 and look at the precise definition. But that's not an AP topic, 2-4, but I suspect there's multiple of us that are maybe thinking of engineering as a potential career field, in which case you'll take Calc 3 and you'll do the heck out of it, use the heck out of that definition and do like real, potentially difficult limit proofs with that. We'll just get a little tiny sample of that and move on about our day, just for some enrichment. Okay, so the definition says, suppose f of x is defined when x is near the number a. Notice that it does not say at a, so we can still take a limit at a certain value of x, even if the function is not defined there. Then we write the limit as x approaches a of f of x is equal to L. That's how I read that set of symbols. The limit as x approaches a of f of x is equal to L. Or you could just say is L. That's fine too. If we can make the values f of x arbitrarily close to L, that's as close as we want them to be, by taking an x sufficiently close to a on either side of a, but not necessarily equal to a. So let's look at a couple of examples here to kind of help us a little bit more understand that definition, because it's a mouthful, right? That's a technical math definition that's like, it sounds rough, but it's not. It's not. So let's look at an example here. So let's say we want to just look at the limit as x approaches 2 of x squared minus x plus 2 is equal to 4. So that's the limit's already done for us. We're just going to talk about like what that statement means relative to our definition. So what I've drawn below is my function y equals x squared minus x plus 2. That's the blue curve. And notice below we've labeled the value 2 on the x and the value 4 on the y. And if I follow my function from the left, as we get closer and closer to 2, we're heading to the value 4, right? And if I follow the function from the right, or from the left, I should say, to x equals 2, it's approaching also the value 4, right? The y coordinate, right? Because the function's output is what the limit is equal to, right? And what our definition is saying is I can pick a value, say, of 3, and that's going to be kind of close to 4, right? And I can get as close to 4 as I want by just picking values progressively closer and closer to 2, right? So if I pick something here, I've gotten a little bit closer to 4. If I pick a value even closer to 2, I get a little bit closer to 4. And I can pick my values as close as I want to 2. Each time I get closer to 2, I'm going to get a little bit closer to 4. That's what we're saying. Do I actually have to be able to get to 4? No. You do not need to be able to actually get there. Does that feel okay, what we're looking at? Okay, we'll do some more examples of graphs in a minute. I just want to do the same thing now, looking at using a table. So pretend we have no picture. So what I'm going to do is I'm going to pick some values for x that are getting progressively closer and closer to 2 from the left side, so values that are smaller than 2. And then I'll pick some values that are getting progressively closer to 2 from the right side. So those are all numbers that are bigger than 2. I'll plug those into my function and look at the outputs. And I notice on each side, the outputs appear to be approaching the number 4, right? We started at 2, then 2 1/4, 344, 371, 385, 397, 398, 399, heading to 4, right? It's slowing down. The change in between values is getting smaller, heading towards, it seems like, an upper bound of 4. Everybody kind of agree that? If I look from the other side, we see the same thing. We're starting at 8, and then 575, and 464, 431, 415, 403, 401, 403. Again, we're seeing the same behavior from the other side, except instead of increasing up to 4, we're decreasing down to 4. Is everybody okay with how we read the table to determine the limit there? Pretty straightforward, right? Nothing sneaky, nothing tricky. Now, as I've mentioned again, it's important to realize that a limit can exist at x equals a, even if the function is not continuous or even defined at x equals a. So if I look at this first example, a here, that's a function that's defined at a, and the limit exists at a, right? The limit there is just L. If I look at example B, I notice that the function is not continuous at a, right? You can see there's a little open circle there. But it is still defined there because it is defined at that point down there, right? We're continuous, or not continuous, but we're still defined at a. And the limit would still exist, right? I can come in from this way or I come in from that way. As close as I want to get to that value, I can, right? And the limit there is still L, even though the function's output at A is not L, right? Okay. And then the last one, or example I have for you here is C. Here, again, we notice that the function is undefined at A, right? There is no, when I did f, if I do f of A, it's undefined. It's an open circle. There's no other point on the line x equals A. However, if I come from the left, I can get as close as I want to L by taking values of x that are close to A. And I can do the same thing that way. Still the limit is L, even though f of A is not equal to L. In fact, there's no value. Yeah, if this wasn't pointing down, there could be no value of x that gives you the output L for the function, and the limit could still be L. Everybody's okay with that? So we feel better about kind of what our limit definition is meaning? It's easy when we see it visually, right? Like that helps a lot, and take those terrible sounding words and be like, oh, I see what they're saying. Sure. Okay, whatever. I can do that. So let's do an example here. So the directions here for these are going to be to use graphical or tabular methods. Let's do both to answer each of the following questions. So I'm going to do, we'll do the first one kind of together here. So one thing I might notice right away, if I look at the function x minus 1 over x squared minus 1, with x approaching 1, what happens if I evaluate that function at x equals 1? I'm going to get 0 over 0, right? Which is undefined. Everybody disagree with that? So right away I know that this is one of these situation B or C, correct? Where Mr. Kulik's probably trying to illustrate this again. So let's fire up our graphing calculator, and we'll just take a look at what happens when I graph x minus 1 over x squared minus 1. So I like to use the fraction command in situations like this. If you press alpha and y equals, that opens up the fractions menu, and you can choose like n over d, which gives you the vertical or that horizontal fraction bar. which I think makes life a lot easier because you don't have to muck around with like a whole bunch of parentheses to make sure you get it to graph the thing you want to. Okay. So we'll do that, and I'm just going to graph this on a standard window. So I'm going to do zoom standard because I don't know when the last time I fired this thing up, and I don't know what my window would be set at. So when in doubt, I just do zoom standard. So if I look at when x is approaching 1, there doesn't seem to be any issue here, right? Let's look a little bit closer, okay? So I'm gonna change my window intentionally to be real close to 1. So maybe I'll go, my x min will be 0.9, and my x max will be 1.1. And it looked like that was real close, or the output of the function there would have been like right near the x-intercept, or the x-axis, right? But it looked like it was on the positive side, so I'll just go from 0 to 1. Let's take a look. You see right there, that little tiny gap. It's hard to see from the back, but if you looked at your calculator on that same window, you'd see a little tiny gap there. That is, and the tick mark here is 1. That is our gap at x equals 1. This is like example C. Right? Okay. So if I look at this, or if I just use my trace function here or whatever, I can do plugging along, it looks like where the y value is right around. I get to 1, there's no y value, I look after it. The limit appears to be, or a half, yeah, 0.5 or a half. Everybody okay with that? Yes.
Like, what's like the difference between like B and C? Isn't it they're both like undefined at like A or? Yeah.
Well, no. B is defined at A. If I did, let's say that this is just like M, we'd say f of A is equal to M, right?
It's not defined.
But here, because there's not a point anywhere on A, here f of A is undefined.
Oh, so there has to be a point there.
Mm-hmm. Yeah. So this is not continuous because you can't draw the curve f of x without picking up your pencil because we have to draw the opening and then the point. But it is still defined everywhere. It's just not continuous everywhere. The second one is not defined everywhere and not continuous everywhere. It's both.
Oh, and then the first one's continuous.
Yes.
Oh, okay.
Yes. 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 Good. Again, have a conversation. If something's not clear, stop and follow up and we can talk some more about it. About what we're supposed to be noticing or whatever, or just general vocab stuff. We need to talk it out, like stop me and talk it out. I don't know what you don't know, right? So tell me and we'll clear it up. Yep. So let's say we want to do this as a tab with a table instead, right? So I would have started the same way. I would have typed in this function into my calculator, into the y equals menu. And then I'm going to use the function operation on my calculator to just do y1 of some values as I'm getting closer and closer and closer to 1. So to do that, I'm going to press the vars button, which is right here under the down arrow. I'm going to go over to the yvars option, pick function mode, and then pick the y1. And now I can do this just like I would a function, I can put a parenthesis, and I can do like 1.1 and press enter. And if I press second and enter, I can recall the same thing I had and pick a value there a little bit closer to 1, say 1.01. And I can hit second and enter and do it again and change that into 1.01. And at that point, I'm pretty confident from above 1, we're heading to 0.5. And I can do the same thing now from below. So I can take, instead of 1, or starting with 1.1, I'll start with 0.9. And then we'll do 0.99, get a little bit closer to 1. And then do 0.999, get a little bit closer to 1. And I'm noticing the same thing is happening here. We're heading towards 0.5. You guys feel okay on how I did this tabularly? And this is the easiest way to do it, is to type it into the y equals menu, use that y1 command, and treat it like a function, just second enter to recall it and update it. That way you don't have to do as much grinding through button pushing and trying to make sure your parentheses are right when you're plugging an actual number into the equation, which stinks. Jacob.
How'd you get the y1?
So I did vars, and then I went over to the y vars, and then picked the function option, and then there's all the y variables from R. And you just need to put a parenthesis around the number, and the calculator will treat it just like a function notation where I'm plugging that number into whatever the equation is in y1. If it throws you an error, probably the problem is you don't have an equation in y1. You just forgot that part. But more often than not, that'll be the issue. Everybody feel good on that? Okay. So the next one, let's try this. So I'm going to put a timer up for, I don't know, we'll do 5 minutes or something. I'll let you guys play around with this and then we'll go through it together. Sound good? Actually, you don't need to see the 5-minute timer. You just trust me that I did it. You don't really care, do you? Probably doesn't need to be on the same screen. It's obnoxiously big. I'll do that. Yeah, what's up?
I just thought of this.
So for this, you're only putting 1 because of the limit is coming into 1, right?
Right.
So like for this, I would do like 0.1 or something like that.
Mm-hmm. Yep,
0.1.
exactly.
Okay.
Yep, exactly. Oops.
They're not like, whatever.
That's not what I wanted that to do. Come on, over here. We guys ready to talk?
Yeah.
All right. What did we get? 0.16. Does anybody recognize that?
No.
1/6. Yeah.
What do you round to?
So you wouldn't.
You wouldn't? Like, you go all the way down?
You want to try to see if it's something that either would terminate reasonably or if it's going to be correspond to a known fraction. Or in some cases, it might be an irrational number. Like you might see something you recognize like pi or e or the square root of 2, which is rough. But that would be unlike for a situation like this where we're kind of estimating, where we're using a graph or we're doing it tabularly, I will tell you in a direction like round to whatever would be okay. But right, but if you looked at the answer in the back of the book, it would say 1/6 there.
Okay.
Hopefully you'd have enough sense to type that in your calculator and go, okay, that's what I got.
There you go, I got it.
Right. Now I would not penalize you for something like that if you,
All right.
with the directions that we have at this point, there'd be no reason to penalize that. Now, did you do that tabularly or with your calculator?
Both.
I did both.
Both. How far did you zoom in on your calculator?
I just push zoom in.
I did zoom.
I just
Okay.
zoom in a little.
So let's do it manually, right? So it looks, this is what I graphed when I just did zoom standard. This is what I got, right?
Why is the line so tiny?
I mean,
I just kept on pressing zoom.
okay. Again, I want to show you something that happens here that can be a problem. So if I did just let's do -5 to 5, and then we'll do -0.1 to +0.3 or something. Hit graph. The window? Depending on how you zoomed, what your window looks like, it may look different, right? Okay. So I zoomed in a little. Still looks pretty smooth, right? Let's go a little bit more. Maybe we'll go to, instead of going from -5 to 5, I'll go from -0.1 to +0.1. Right, getting real close to 0. Okay, flat line. Mr. Kulik, what is the issue? What if we zoomed in even more? What if we did -0.00001 to oops, I wanted one more 0 there. 0.00001. Yeah, okay. So change that to a 6. Hit graph. Oh man, it's not gonna do it. You stupid machine. Okay. Well, it shows me. So here's the concern. Okay. Where did that go? Where did I?
Because I have the same thing, it's just like, I didn't zoom in. Well, yeah, because see how mine goes like to the white equals zero, that's what yours is doing, I just didn't zoom in.
So if you had depending on, again, the amount of memory on your calculator, the software that you're using, look at what we got. What happened? Why did we get this odd result? Why is this happen? Why could this be happening?
Because of limits. Because of limits.
It's a calculator problem. What's the matter with your calculator? Why is it having such trouble zoomed in this far? We're the computer science people in the room.
Not me. That's not me.
Okay.
Code.
I'm a computer science kid.
Okay.
Last semester. No, last year.
That's okay.
I did it 2 years ago.
Think about what
The bytes, bits.
think about what has to be stored to do this. How many decimal points are these numbers going to be with that much zoomed in? Well, that's 10 to the negative 6th and then 10 to the negative 7th. So
I would say about 15.
yeah, so how many you know how many decimal points your calculator stores?
Oh, let me guess. 9.
But it can actually store more than that. But yeah, what's happening here is that the calculator is like it terminates the decimal at some point. It doesn't keep all the decimal places. When we've zoomed in that far, everything is just like truncating off the end. So like on this one where it looks like everything goes to 0, that's because all the decimal points preceding what it can store were all just zeros. Right? I think you can store 99 decimal points on your calculator.
99?
So like zoomed in this far, all of these values have 99 zeros before they get to a number, but the calculator truncates it at 99, can't store more than that, so it's just all zeros. So the moral of the story is be careful with the calculator when resuming. The tabular option, you wouldn't get this because unlikely you're going to go, okay, 10 to the negative. But you might keep hitting zoom for a long time and end up running into a situation like this where it just kind of like zeroes out on you. Does that make sense as to what I'm trying to point out to you? Okay. But the answer here was 1/6, which it sounds like most of us got, right? The 1 points or 0.16 or 0.17.
Would we have to like turn the decimal to a fraction like that, or just
I'm just telling you that's what the back of the book would say if you're checking an answer.
0.
But like hopefully just have enough sense to like type that fraction in your calculator and be like, that's the same decimal I got. Okay, good enough. Right. All right. Let's try. Oh, can I point out one thing to you? No, let's not do it now. No, we'll wait. We'll do it next time. Should we try the next one? Where's my other little guy? Did I lose him already? I probably did. The dumb I am. I know this is covering everything. I'm going to move it in just a second. Yeah, same instructions, different problem. Good. Hi.
So when I'm doing like the tabular way, wouldn't it just be better to do this and then you get the exact answer of what it is instead of doing like y1 and then like 0 point, like with all these decimal places?
Okay.
Because you're gonna get really close to here, right? But then this is what it exactly is. So
No.
what, you don't. Oh, you don't do that then.
This is just going to be. This is going to be using whatever is. We forgot the sign.
Oh, I did.
What that's doing is your calculator has a value already stored in for x when it's just written as something like that where it's not inside of a function. So all it did was take pi and divide it by 10. That's that number.
I see.
You have to have the variable inside of a function for it to treat it as,
Okay.
you know what I mean?
Yeah. All right.
I don't like, do we have to do graph version on the test?
So what if all I give you is the picture of the function? What if I don't give you the equation?
Then we'll have to.
Then you'd have to, right? That's why we're practicing.
I'm the opposite, I like the graph. I can't figure it out, I just like don't know.
Pierce, I typed that in wrong, by the way.
Oh, you're right. You're right.
Oh, you're doing this one. We're supposed to be doing this one here. Sine x over x. Oh, okay. That's an excellent question. Radian or degree?
Degree, or does it matter?
I think it depends on degree.
Oh, degree. Wait, no.
Is it radian? Wait, for number 4.
Oh, well,
would it be
depends.
in radian? I'm just kidding.
So it's,
Or no, it's radian.
4 is radian, 4 is radian.
Yeah, 4 is radian.
Well, this one's degree.
Yeah, but 3 is degree.
I would say it doesn't matter
Oh, I said that.
other than you have to be careful about your window or your scale when you're graphing. Right? If you're doing degrees and you're trying to look at a graph, you shouldn't be using like negative 2 pi to 2 pi. You should be using negative 360 to positive 360, or else you're not going to get the right picture. In general, I would do everything in radians. In general, in AP Calculus, I think almost everything is going to be given to you in radians. I'm trying to think if I've seen anything not in radians, and I don't think I have. Just put in radians and keep it there until physics class, and then make sure you switch it back after you do your physics homework.
I had my different answer when I read. I got like, what?
0.99, and then I switched it to degrees. I got, wait, can I see it? 0.17.
Mm-hmm.
So should I keep the degree then?
Um,
Well, like I'm doing the right.
Because they're really different.
Like, because you had a space.
I'm in degree.
no, it shouldn't.
It should be different?
No, I mean, like, the number could be different, but your answer for the limit should be the same. The individual tabular values you get
Oh, like,
It's gonna be different.
could be different, because like sine of 0.1 as radians and sine of 0.1 in degrees are two different numbers.
X going to 0.
It shouldn't matter the mode, though. The limit should end up being the same thing. If you look at the pattern of those numbers,
Okay.
it should be the same.
Okay. Thank you. But like,
Does that
Basically, when you just
answer your question? Kind of?
just like, yeah, when you like, or like this.
Yeah.
Yeah. You just like tested a couple of them for all your different.
I don't know. I'm having trouble with Bex also getting like different answers. But when I did, this is when I switched it to a radian mode, and I just get 0. So I don't know like what happened there.
Yeah, that's why I picked these. That's why we picked these problems. It's there.
Oh,
Like
it's
weird
a-
things can happen.
Oh, okay.
So you have to be careful about what you're doing. That's
So just keep it in degree mode then?
no, I
Or
don't.
use Radians for the.
What mode are we in?
I'm in degrees now.
So I would say that this is just probably too fine of a grain to get what you're looking. Oh, there's my timer. So we'll go back and we'll talk about. Or which one are you looking at? 4 or 3?
That's
Okay,
4.
we're not even into 4, so just pause on that. But yes, I've chosen these because weird things can happen.
So I was just wondering. 'Cause
Uh-huh.
I did these in degrees, and I got the 0.017, and then I did it in radians and got that. How would I be able to deduce the same limit from those? Oh, is it because it's 0.01 and then point? Wait, no. That doesn't make sense.
What?
So do you know how to
For three.
Sine of 0 is the same in either one.
Yeah.
No, you're
Put it into a limit. Like
And we're
what do you do
going
with
to,
this?
oh,
This number is the limit.
so if we did this, and we're in degree,
Is the limit function there when the number So isn't the f of x to 0.017 as x approaches?
that's odd.
It's like the Y.
Let me think on this.
Okay.
Okay. Let me think on that, why that's a problem.
Wait, so this is the number that's gonna go after like f of x in the limit notation?
Yeah, what we're finding out is like you'd write equals what here, and that's the number we're finding.
And then I don't get how like the radians and degrees, it's gonna give us different
okay.
numbers, but why are they equaling the same?
Okay, I don't know. Hold on, let's just back up because a bunch of people have asked about this. Just do everything in radians.
Okay.
In this class, just do it all in radians. I'm trying to think about why that's coming out to be different in this context, which is the one that I'm having, is what I'm struggling with as to why that would matter, because sine of 0 in radians and sine of 0 in degrees is the same value. But and both of them should be I don't know. I have to think on that why that's and it could be a decimal thing on your calculator still, which is stupid, but all right. So if we did this, I'm gonna zoom trig this. Oh, and I'm in the wrong mode. Put that in radians. Sine x over x. Oh, well, what is this oh, it's because I zoom trigged it then. Okay. There. Okay. So here's my graph. This is just in radians with zoom trig. Looks like we're heading towards 1, right? If I zoomed in a bunch, nope. What might I notice? We're going to have to, real quick, I'm going to turn my axes off and point out to you what you probably already knew. Oops. What do you see? Oh, right. Which shouldn't be surprising if it's sine x over x. If I plug 0 in for x, I get something over 0, undefined, right? But we should have gotten 1 there. All right, let's try 4. Do the same. Yes,
You have to-
absolutely.
We'll send you a list of this.
You guys have to start like funding this stuff.
Yeah, we'll send you this.
Box of
Or
cereal is
addition.
$9. Cost like $3.
Are you reading? Yeah.
Oh, no, it's got the squiggly thing.
Oh, I do.
What is this? Oh, what do I do?
Oh, wait, why?
Just to like a low key
I got zeros.
Yeah, you need to borrow one. I got extras. Should have said something.
Well, I was looking up there.
It's just starting to get annoying because it's like I actually kind of want to be able to do this myself.
Yeah.
For sure.
Before I got to it.
I don't know. What do you do if you keep getting zero, or is that like the point of this?
Hmm.
Oh, wow, look at you, man. You got she's in that.
Yeah. So think about why you keep getting zero when you're trying to do this tabularly.
Because of itself, right?
Wait, Mr. Willie gets it because it doesn't exist, or does it exist?
Wait, is it rack?
Well, I mean,
No way.
that's not the reason why they keep getting zero, but that could be what's going on here.
Isn't it not a function?
Nope, this is a function.
Or doesn't it fail the vertical line test?
No.
I'm gonna try to do this. How do you guys delete zero?
Yeah, that's what I got.
See, I was looking at the graph and I was like, I don't know what to trace in this.
Yeah.
What am I looking for?
Wait, let me see it. Wait, what is it?
Wait, run example 4, right?
I just noticed that like it didn't touch zero. It was like this.
Sure, zero.
Yeah, I just put zero. I was like, okay. Why are you laughing?
Should we stop and talk about this? Seems like everybody's kind of confused, right?
It's not even sure. It's just like,
Okay. So when you guys tried to do this tabularly, which is what it sounds like most of us started by doing, right? Which is good. That's fine. That's a good start, right? You did like y1 of 0.1 and you get 0. It's like, well, that's okay, whatever. And I tried doing 0.01 and I got 0. And really anything I typed in here, I was getting probably 0, right? Which is like, why is this happening?
Because it's the only point it doesn't cross.
Think about this. It's a unit circle answer, which is a
Too
frustrating.
high.
Where is sine equal to 0 on the unit circle?
No, it's 2 pi.
0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi, etc., right? Everybody agree with that?
yeah.
Yeah.
So when I'm putting in like 0.1, I'm really doing sine of 1 over x, or I'm sorry, 1 over 10 over 1 over, oh, I'm sorry, I'm putting this in the wrong spot. I'm doing sine of pi over 1/10, which is equal to sine of 10 pi, which should be 0. So as long as you're formatting your input as 1 over a number, like 0.1 or 0.01 or 0.001, which is just like 1 over 10, 1 over 100, 1 over 1,000, you're going to keep getting 0. If you had tried doing instead, I think if you do this, you start getting numbers. Because 0.03 is not a unit fraction, right? That's 3 out of 100 or whatever. However, is that going to help us any? So I do that again, and I just keep getting the same value again. Why is that happening? Unit circle. You're just traveling one like period and getting the same value again. So this one is really difficult to do tabularly because our instincts would tell us to do this systematically, right? So at this point, I'm frustrated. I'm going to throw the tabular option out the window because it just feels like it's going to be trying to cram a square peg into a round hole, right? So you go and you look at the graph and you go, okay, well that's I can't tell what's going on near zero there, so let's zoom in a little bit more. So maybe we'll go from like negative 0.5 to positive 0.5. And we look at that and it's okay. Well, if I look even closer there, I mean, it kind of looks like it's crossing at zero. Like it kind of looks like a, but we probably have to zoom in a bit more. So but it's getting really staticky. But I keep zooming in, and it just gets more. Shh. Guys, listen. So we've thrown out the tabular option, right? Because it feels like it's just not helping, right? We can get numbers, we can get zero, but it's a problem. I try graphing it and zooming in. As farther I zoom in, the statically, you know what I'm trying to say. Fuzzier it gets, right? What's going on here?
Calculator. Yeah. Calculator.
Different than undefined does not exist.
So if it equals 0, does that mean that it does?
Nope. No. I was just illustrating to why that does not exist means it does not settling down to a single value. The closer I'm getting to 0, I'm still getting wildly different values, and there's no pattern emerging as I'm getting closer to 0, right? We're not getting closer and closer to a single y value as I get closer to 0. It's still just bouncing around.
And then what's going to be like undefined? What would that look like?
So limits aren't undefined.
They can't be.
A function can be undefined, but the limit is either going to exist and be a number or infinity, or it will not exist. In what case like this, it's just oscillating too much. The closer we get to it, it just keeps bouncing. There's no pattern that it's settling down to. And now I didn't tell you that was an option, so that's okay. As you did exactly what you should have done. You tried doing tabular, you kept getting the same value, and well, I'm not doing this right. You were doing exactly what you should have been doing. The problem was that this one wasn't going to let you do it that way. You looked at the graph and you looked at it and it's like, well, that's a mess. I don't know what to do with that. Great. That's exactly what you should have thought. And the answer is something that I hadn't told you was possible. It's just that it doesn't exist. Right? Mean Girl fans?
I was really thinking about that.
Yeah. There you go.
Yeah.
All right.
That is like my.
I think I'm going to skip this one. We're taking a lot of time here. I want to get through the rest of this stuff. I'm going to skip that example. So one thing we have to talk about here are one-sided limits, which we've already done. So if you remember where we started here, those two are each a one-sided limit. This one is like the left hand, and this is the right hand. Because x approaches a from the left, negative a to the negative is saying the number's smaller than a. That's your left side. And A with the plus is telling you the numbers that are bigger than A, so that's the right side that you're approaching from. So we've already kind of seen this. So let's look at what's called this Heaviside function. So we're going to define it as 0 if the t is positive, and then it's going to be 1 if t is, if t is negative, it's 0, and it's 1 if t is non-negative, so 0 or positive. And if I want to evaluate the limits, what is it if I'm taking it from the limit as t approaches 0 from the left, from the number smaller than t? What would I expect that to be? Should be, so I'm taking all my values are coming from this side, right? So it should be 0.
Can it not be equal?
Can be equal, right? As I get arbitrarily close to 0 from the left, every one of my outputs is 0, right? Is that okay?
Yes.
Okay. And what would the limit as t approaches 0 from the right be then? 1, because every t I'm taking comes from over here. What do you notice about these two limits? They are different, right? They are different. So that is important. One way that we say, or one way we define a limit, so we say the limit as x approaches a of f of x is equal to L. That's a limit existing. If and only if the left-hand limit and the right-hand limit are equal to the same thing. And that number is finite, or is defined. That number exists. So in this case, we would say the limit as t approaches 0 of h of t does not exist, because the left-hand limit and the right-hand limit at 0 are different. Yeah, so we'll say the limit as t approaches 0 of h of t does not exist, because the left-hand limit and the right-hand limit are different. So that's another way that a limit may not exist. We can have a situation where it's just oscillating too quickly for us to understand, like it doesn't settle down to anything. Here, the right hand settles down to something. The left hand settles down to something, but they're different. Which one should be the limit? Neither doesn't exist. Prater.
Can you explain how we didn't know?
Yeah, so if you looked at, right, so you did all those tests, but if you look at the graph, this is like really far zoomed in, and it's definitely not heading to 0, right? So using a combination of the graph and the table, you should always, you should never do just one of those two. You should always do both and make sure that they match, because here's a situation where the table might lead you to believe one thing, and the graph disagrees. The previous one, if you zoomed in enough and had enough accuracy, the graph did one thing, but the table did something different, right? So you want to make sure that they're matching. That's kind of the idea. Is that?
Yeah, that makes sense.
Okay.
I just didn't know how to develop.
You should check both if both are available to you, right? Like if it's a no calculator and it's like use this graph, you're fine. Just use the graph. Or if it's just giving you the table, just use the table, right? Like if I just say, here's a table of values for some function f of x, you can't graph anything, right? Like that's all you got, that's all you need.
If they disagree, just say it does not exist.
Right, yeah, that would, or well, you have to be careful, right? Like we saw this one, we only had, everything was fine, we zoomed in too far, and then the calculator failed on us, right? The graph really matches what we did tabularly, unless you start off too zoomed in and then you got like weird answer, right? Okay. So let's take a look at this example here. So this is the sort of situation I was talking about. Here, you're given only a graph of a function g of x. You're not told the formula for g of x, so you can't plug anything in and do anything tabularly, right? All we can do is look at our picture. All right. So if I look at A, the limit as x approaches 2 from the left should be, what should that equal? Excellent, right? Because you're just following it up. Looks like it ends at 3. Yes? Did no calculation. I just followed the graph from the left to 2, and it appears to end at 3. Right? That's all I'm doing. How about x approaches 2 from the right? Good. And how about just limit as x approaches 2? Does not exist. Great. Why not, Prater? The left and right limits are different. The left limit is 3. The right limit was 1. The limit at 2 cannot exist. Okay. All right. The limit as x approaches 5 from the left is, looks like 2. Good. And the limit as x approaches 5 from the right, or from the right. Also 2. So the limit as x approaches 5 is 2. But what is g of 5 equal to? Looks like 1. So note the function actually evaluates out to something different than the limit. And that's fine. Not a problem. Everybody's okay?
Yes.
Okay.
Will no point always be there?
No, it doesn't need to be there. If that was not there, it wouldn't affect anything. Yeah. I just guesstimated it. It probably looks like more than 1, but like whoop-de-dee-doo.
Yeah.
All right. Infinite limits. So we say the limit as x approaches a of f of x is equal to infinity if both the left hand and right hand limits go to infinity. Right? So if I look at 1 over x squared, I notice that I have both the left-hand limit and the right-hand limit at 0 going to positive infinity, right? If you did that tabularly, you'd see the numbers getting bigger and bigger and bigger and arbitrarily as big as you want the closer you got to 0. And the same thing would happen at negative infinity. If I did negative 1 over x squared, they're both pointing down, negative infinity. If we go back to here, what would we say the limit at x approaches a is, though? Prater? Does not exist. Why? Yep, the left-hand limit is negative infinity. The right-hand limit is positive infinity. Those are not the same. Does not exist. Okay. So all we're going to say now is that we can define a vertical asymptote using a limit. We say that something has there's a vertical asymptote there if either the limit is positive or negative infinity, or either side, either handed limit is positive or negative infinity. If just the left-hand limit is positive or negative infinity, that's a vertical asymptote. If just the right-hand side is positive or negative infinity, that's a vertical asymptote. If either side is, if both sides are the same or both are different, it's a vertical asymptote. That's all this is saying. So whenever you have an infinite limit at a finite number, that's a vertical asymptote, whether it's from one side or the other side or the limit itself. In the interest of time, we're going to skip this and just tell you what the problem set is. So remember, what do the bold ones mean?
Class.
Those are the homework quiz numbers, right? That would be Tuesday in the next class, yes. And will you have to do this by yourself? It is open homework, so bring your homework assignment, and you'll get someone else to work with, for sure. Make sure you do the bold ones at minimum. So 9, 11, 13, 17, 21, 23, 29. So that would be the easiest way to do that is if you're opening up the digital textbook, the PDF. It has the table of contents built in if you open the bookmarks. And you can just go like 2.2 and then just scroll to the end. So mine says this is page 96. So you could skip to page 96. If you're someone that wants a paper textbook, let's take care of that right now. Just if you look at the last set of cabinets, those are all full of paper textbooks. Grab a book and then come show me the number. Wait.
Do you still want us submitting all our homework on OneNote?
That's where we'll turn in the weekly problem set. Yes.
Is it easier to just do it on the computer or do it on paper and take a picture?
Whatever works for you, man.
Okay.
I'm happy with whatever you want to do. A lot of students last year would screen grab the problem into their OneNote so they didn't have to worry about copying anything on a sheet of paper, but a lot of people did on paper too, so it's whatever works for you, man.
But for when we're doing the homework, we'd be able to use our homework on our
Sure.
tablet, right?
Yeah, of course. Of course.
Where do you, how do you do Mr. Cook, can I see the homework problem?
Yes, of course.
Oh, if you didn't know. And then I click this at the top and then you go.
I kind of just missed this part. I don't know if I have this written down right.
Yeah, if so you have a vertical asymptote at A, if either the left-hand limit at A is infinite, positive or negative, the right-hand limit is infinite, positive or negative, or just the regular limit at A is infinite, positive or negative.
What do you mean by regular?
So just like x approaches A
Oh, okay.
would tell you that's an asymptote.
Okay.
Or if x approaches A from the left is infinite, that's a vertical asymptote. Or from the right, it's a vertical asymptote.
Okay.
Is that
Yeah.
okay? Hi. How are you?
Good, how are you? Should I join this?
So yeah, go ahead and click it, and then you'll go class notebook.
Or this is fourth hour, so should I say?
Oh yeah. I thought I signed you up. It
Maybe
didn't
my
come in.
computer just slowed. Oh, just
Yeah,
loaded.
okay.
Sorry. Thank
That's
you.
okay. I was like, I did this morning when I saw that you had added. I was like, I thought I did it. Hey, if you're taking a textbook, I need your number from the title or from the first page or two. There's a number inside the cover.
Yeah.
Read that to me.
140360.
Great. Thanks, Rita. Certainly. You're welcome. And you are, I think, the next page. There it is.
Oh, 140.
Hold on one second. I gotta find your spot. Okay, 140
354.
354. Okay.
Oh, wait, yeah, how do we know what page it's on?
Well, it's the section 2-2.
Oh, 2-2.
Right, so it's just the homework at the end of 2-2. I don't know, like 128 or something, I think.
Yes, they had that.
I guess so. So I think this page. What's the number? Hold on 1 second. 1 4
140
344. Thanks, Tessa. You're welcome.
They were all out of the first spot. So is lunch one day? Lunch one is before, lunch two is lunch two. So lunch one is the same though. Lunch one is last one after community time. And then now